In this lecture, there are two examples on rate of climb. We are going to evaluate rate of climb for prop and jet. Here is familiar aircraft from Anderson. We will use all this data. We will need propeller efficiency as well. So here is sample calculation. Calculation is for sea level. Here is standard equation. Excess power divided by weight will give us rate of climb. Excess power is power available minus power required. Now we have to calculate power required for this particular velocity. We've done it many times before. So out of given velocity and density, we can calculate, and weight of course, we can calculate CL, then we can calculate CD, and then we calculate power required. Now we have to calculate power available. So power available will depend on efficiency, propeller efficiency, and power plant. And we get it in horsepower. We have to convert horsepower into feet pound force per second. Here is conversion coefficient, 550. And then we calculate rate of climb. It is in feet per second, and we need to convert it into feet per minute. This is due to aviation regulations. Then we repeat this calculation for other velocities of interest, and then we plot it. So here is plot rate of climb versus true velocity. And here is maximum rate of climb. With associated velocity. I'm just sketching it like this. Now we are going to analyze jet. Again, familiar data. We will start with calculation of maximum rate of climb. You obviously see that if we try to do it graphically, it is not that accurate. We want to calculate it exactly. So I'm going to take our previous derivation, and here we can estimate lift coefficient, which will be associated with maximum rate of climb. So we find this lift coefficient. Please double check this solution. It is assumed that you will calculate it yourself as a practice. Now we make a little assumption. We know that in climb, lift is less than weight, but it will bring additional unknown into the picture. We don't know angle of climb, we don't know velocity, and we don't know angle, two unknowns. So if we rewrite this equation, we will get weight cosine theta equal to 1/2 rho v squared SCL. You see, we don't know angle of climb and we don't know velocity. So we are going to assume that angle is small and lift is equal to weight. We remove unknown angle from the equation right now. It will come back later. So here is familiar equation. Please substitute data and please calculate velocity. It is on the next page. So we find velocity. Please double check. Now we are going to find drag. We know everything here. We can find drag, and after that we can find rate of climb. We express rate of climb in two ways. It is vertical component of velocity and it depends on angle, unknown angle of climb. And also we can find it out of excess power. So out of this we can find both unknowns, we can find rate of climb, and after that we can find theta. Here is the result. Once again, please double check. Please solve this problem yourself as a practice. On this page, we have calculation of rate of climb curve in the same manner as we did for prop. So we are given velocity, we are at sea level, we calculate power required, and you know how to do it. We get power available from given data and calculate rate of climb. That's for this particular velocity. Please don't forget that we convert feet per second into feet per minute. In the same manner, we calculate rate of climb for other velocities of interest. Now we can plot it. So here is curve, and here is maximum rate of climb. Associated velocity was 572.8 feet per second, and we found it before in exact way.